Okay. All right. Well, I'm Craig with Blue Planet Environmental Systems. I'm actually the president of Blue Planet Environmental Systems. I started it in 1997. I grew up working for companies that sold and represented equipment like this. So I was a service technician for many years, and I decided to start my own business at one point in time. And along the lines, it was pretty much somewhere right around 9/11 that I primarily got into what we do now, which is only chemical metering skids. Back when I started, I was a service technician, and I would work on chemical metering pumps or gas chlorinators, gas ammoniators, just whatever type of equipment. And after 9/11, when everybody started switching from chlorine gas to sodium hypochlorite, I was helping my customers do that, and I saw a lot of problems. And basically, it was a misapplication of the pumps. I think a lot of people back then, and I consider this too, when you consider all the different chemicals we deal with and the different systems I make chemicals for, sodium hypochlorite I consider pretty safe, right? It's not like we're dealing with sulfuric acid or fluoride or something. So from a danger standpoint, none of us would want to bathe in the sodium hypochlorite that's delivered to this tank, but it's not like if we got a drop of it on our fingers, oh my God, I got to run right to the safety shower. You're probably going to rub it off on your shirt, and your shirt's ruined because you're going to have a white spot on it next time you wash it. But that's the end of it. So from just a safety standpoint, not a super, what I would consider dangerous chemical, but it's actually one of the most difficult chemicals we have to pump with or to deal with on a metering pump. And this isn't a chemical metering system. I'm just getting into that to explain how I got into what we do now. So basically, I just wanted to make sure that we were recommending the right pump, that the installation was correct, and again, then I would start to see problems there, because if you go back 20 years ago, you would never even see a chemical metering skid. On a big project like this, Wharton Smith would have gotten quotes from a bunch of people like the companies I used to work for, and what they would have done was sold them pumps. Everybody would want to sell them pumps, so they would have a bunch of people bidding them, use my pumps, and the guy that would sell them the pump would sell them all these little devices we're going to talk about here in a bit. So they would get all that stuff in a box, and then it would be up to the plumbing contractor on this job site. They would come in here and do the plumbing. And it's not that plumbers are not experts in their field. There's some really great plumbers out there, but chemical metering systems a lot different than drain piping or potable water supply piping. So on all these little components, it's really critical for them to work as good as they can, that they're installed in the right location. And most plumbers they don't realize that. They would come out here with these boxes full of equipment. They're looking at a schematic, which is kind of like a pencil sketch showing, here's a pump, here's this, here's that. And if you handed 20 different plumbers the same equipment and the same drawing and put them each in a different room, you'd have 20 different systems. Some of them would be pretty good, some of them maybe not so much. So anyway, that's how the whole skid concept came to be, is I was thinking, how can I make sure my customer gets a good installation? So basically, that's kind of where the skid idea was born. We can design this, we can lay it out, we can make sure we've got the right pumps on here, we can make sure all these safety devices are installed where they're supposed to be. I try to think about the service guys, just coming from my service background. Since the first skid that we ever built 20-something years ago, every pump on every system we've ever built has its own flushing point on the suction and discharge side of the pump, so that when a maintenance guy comes out here and needs to work on it, that's something that would always blow my mind, especially with a really dangerous chemical like sulfuric acid. I'd be looking at somebody's field plumb system, and I'm just studying it, and I'm looking at unions, and I'm looking at piping, and I'm thinking to myself, holy cow, man, what does the maintenance guy do when he has to work on that pump? Because these are maintenance items. And you'd ask the guy, and he'd say something like, oh, usually what I'll do is I'll kind of put a bucket here, and I'll put all my safety gear on, and I'll just crack that union, and I'll stand back until it stops leaking, and then I'll get in there and I'll sop it up, and stuff like that is just crazy. So we wanted to make sure we've got a point on our system to where your maintenance guys can come out here. They can either put a bucket under this valve, or they could screw a tubing connection on this threaded thing with some hose, and they could slowly open this valve and they could drain the chemical out of the system. If they want to take it a step further, we've got a second access point on the suction side. You could isolate this pump from the system, set a bucket of water here on the ground, and you could actually pump water through the pump and the piping. So now when your maintenance guy takes this stuff apart, everything's been pre-flushed. So, just a lot of little things that go into this. without, you guys have been running skids and running pumps for a while. Before I get into all my stuff, does anybody have any general questions or?
Do you have, we probably asked you this before over at Silver Spring Shores when you went through your presentation there. But is there any way, I know that you've got the drawdown tube available. Is there any kind of way that you could put some sort of maybe like a sensor of some sort, like when you're running two pumps, one as a backup?
Right.
Like for example, if one starts to not fail, but
it's not pumping anymore.
Yeah. Where the other one might take over.
Yep. Well, the only way, unfortunately, the only way you can do that, but we would have to add external instrumentation. So at your other plant, we're using the same brand of pumps. They're made by Prominent, but they're a different model. They have motors, I'm pretty sure, at your other plant. But in any case, the pump itself has a lot of capabilities in it, and there's a whole bunch of signals that we're sending your PLC through this box right here. So this pump is telling your PLC how fast it's running, and it's actually pretty slick on these Prominent pumps. It's even tied into the stroke knob, where most pumps don't do that. If an operator would come out here, say you're running this pump at 100%, it's going to tell your PLC, I'm running at 100%, should be getting 7 gallons an hour. If someone would come out here and mess with the stroke knob, the motor would still be running at 100% speed, but they could crank the stroke knob down to 50%, let's say. So your pump's still running, but it's really running 50%. Most pumps would still be telling the PLC I'm running at 100% because that signal is only based on the motor speed. But on these pumps, they have a stroke sensor in here that also feeds that back. The problem is the pump truly doesn't know it's pumping, which is my long-winded way to your answer. This is the pump telling the PLC, I should be feeding 50% right now because my motor's at 100% speed and my stroke link's at 50%, but it doesn't know whether it's pumping or not. I could close a ball valve and this pump's not feeding anything, and it would still tell your PLC I'm feeding 100% or 50%. So what we would have to do is put a flow meter on the discharge of your skid, a magnetic flow meter. And depending, I can get with you guys on that. What we need to do, it's really hard. It's really hard on chemical metering systems. There's some pretty good flow meters out there that are relatively cost effective, but if your flows go too low, you're looking at a real expensive meter for two reasons. One is compatibility. It's not a water line, it's a chemical line, so we got to make sure like the electrodes have to be titanium and the liner has to be Teflon. But the other problem is the flow rate is so ridiculously low. This is a 7 gallon per hour pump. This is 1/2-inch piping. I'd have to run the actual calculation, but this pump at maximum speed, I guarantee you, is feeding way less than 1 foot per second. And we're not going to be feeding at maximum feed. We're going to be feeding somewhere down in the middle. So the flow velocity is so low, you need a magnetic flow meter with a really, really tiny orifice that can measure super low flows. But there are some out there. So what we should look at your other plant, if you guys can get me some information, maybe from your trending charts, let's see where your pump's been running, where the highs and the lows are, like gallon per hour wise. And if I can get that info, I can look into what kind of flow meters are available. And with that, we could have a flow meter on the discharge. It would actually be measuring the flow of the pipe, regardless of what the pump thinks it's doing. And then this would be bringing the PLC guy in. That signal could go to the PLC, and he would say, yeah, I'm feeding 3 gallons an hour. And if the middle of the night that 3 started dropping down, he could have an alarm point set up where, hey, I don't know what's going on. This pump's dropping off the curve. Shut this pump off. Turn the other pump on. So it could be doable, but we would have to add extra instrumentation on that. That they actually already have, they should already have that capability built into the PLC through the pump's fault signal. These pumps also, this orange cable on all your Prominent pumps, these are inputs. These are signals coming to the pump. So this is where the PLC is telling it, start, stop, speed up, slow down. Your gray cable are the signals coming out. And basically what we're telling the PLC is this is how fast I'm running and a fault signal. So this pump has internal diagnostics. It'll trip a fault if it thinks something is wrong. One of the faults it could trip is if it thinks it's totally vapor locked, totally feeding air. But that's kind of like, there's a lot of scenarios between being vapor locked and they're not pumping enough for you. But in any case, if any internal fault trips on this pump, the PLC knows. Now, we'd have to get with your PLC guy to find out what kind of programming they have. So I don't know if all the PLC guys is going to do is tell you there's an alarm, you have to come out, you have to see what the alarm is, you have to switch a pump over, or if they're going to have it set up where if a pump faults out, it automatically turns on another pump. But that's a possibility too. The only thing that you have to do there that you have to think about, unless we're getting into adding actuators to your valves, which you don't necessarily have to do, but if you're feeding one critical point, we could have both of these pumps, we could have them all primed, all ready to go. We could have all these valves manipulated where both of these pumps are going out this pipe. This is my critical point. So nobody would even have to come out here and manipulate a valve. If you had your skid and your valving set up that way, the PLC could have that pump off and it could have this pump running, and if it would see a fault from this pump, the PLC could simply turn this pump off, turn that pump on, and this pump would start going on the line, and nobody would have to manipulate a valve or anything. But again, to do it based on actual flow, we would have to add a flow meter on the common discharge line.
Just one? Oh, okay.
Yeah. I'll make a note to get with you guys and see what your flows are at that other plant. If there's something we can do to add a flow meter, we can look into it. So is that a problem you've been having over there? Has the pumps?
I think he's thinking just scenario-wise, but you got to remember that Silver Spring Shores is not true flow proportion control, but yours is. Oh, okay. They don't have that, so they're putting it at a set point and letting it run. Whether it's an 11, whether it's a 3 residual.
Oh, so it's totally adjusted by the operator depending on time of day. Or okay, yeah.
Scale where flow proportion at Stonecrest and Oak Run is based on its set point, flow, and what the residual is combined.
Right.
And that it's actually controlling the pump, slowing them down, increasing them.
Yeah. But at Silver Springs, it's not even flow paced. It's totally manual.
It's totally manual.
Wow. Yeah, that's hard. Well, flow pacing is easy. I know we're getting off subject to training on this skid, but it's good general discussion anyway. Flow pacing is relatively easy. When you get into residual control, if you combine residual control and flow pacing, that's called compound loop. But residual control would be, I want to be able to say, I want 2.5 parts per million. That's residual control, being able to pick a part per million. Yeah, okay, well flow pacing is just, I'm not necessarily telling you I want 2.5, but it's like your flow's coming through your plant, your flow varies. If you're here at a certain time of day where your flow is relatively constant and you can play with your pump and you get it dialed in just where you want, you say, man, this is perfect. My flow's at whatever and I have 2.5 parts per million. Flow pacing would be, okay, take that information and now when the flow goes down, feeds less. When the flow goes up, feed more. That's flow pacing. So in that scenario, if the flow would cut in half, the pump would cut the feed rate in half. If the flow would double, the pump would feed twice as much. For most plants, in all honesty, flow pacing is adequate, even more than adequate, because we're feeding the chlorine at the tail end of your plant. It's gone through so many other processes to where even if some type of weird hit came in at the front end of this plant, right? Who knows what it would be, but some industry or whatever, all of a sudden you get hit with something weird that kind of off balance, upsets things a little bit. Usually by the time it gets to the tail end of your plant and the contact chambers, that's all kind of settled out in the wash, right? And it's still relatively stable. So in most instances, flow pacing only can do very, very good control. So at your plant where you don't have flow pacing, you probably have a flow meter, you know, where you're injecting. The problem is right now they're just not running that signal to the skid. So if you could get that actual signal to the skid out there, the skid is definitely set up. It should be, but the skid should be set up to take that signal. So if we could get the PLC guy or somebody to actually run a cable out to the skid that has the 4 to 20 signal based on flow, we should be able to hook that up to the skid, play around with it, try flow pacing and see how that works. And you might find that's all you need at that plant, or that it's a lot better than it is now, because what you guys are having to do now, if you don't have even flow pacing, is in the wee hours, your night operator knows the flow's getting ready to come down. He's sitting there, and probably what happens is, oh crap, the residual's starting to come up. So he goes down, and he's got history in his head. He knows what to do. He'll bump the feed rate down. But there's probably an hour, couple hour period where things are out of whack a little bit because you're kind of playing catch up, and then things settle down, and then in the morning he has to pick it up.
Well, I might have got off the topic. I'm sorry. It was just something.
question.
No.
It was going through my mind
Yeah.
about maybe if the screen or something was starting to get some sediment in there in the middle of the night, maybe the pressure.
Right. Well, it can all be done, but like I say, unfortunately, it has to be done with external instruments. The pumps themselves, they're getting smarter and smarter. I mean, the new pumps they're pretty crazy compared to when I first got in it, which all they did, you turn them on, you turn them off, you speed them up, you slow them down. There's crazy electronics in here. They're monitoring a lot of stuff. I wouldn't put it against one of these guys sometimes in the future to come up with some type of way where they put a sensor in their head where the pump now knows how much it's feeding, but as of right now, nobody does it I'm aware of. So to do something like that based on flow, we would have to have a flow. And there's other things that sound really cool, and I get into this with instrumentation salesmen all the time, because I'll go to like a trade show, and there's a guy that's got all kinds of impressive instruments. So he's got pressure sensors and flow meters and switches, and I'll walk up and go, hey man, you got flow meters, right? Oh dude, I got the best flow meters ever. I'm like, well, cool, you got any low flow meters? Oh dude, we can do crazy low flows. And he'll show me his smallest flow meter, and his smallest flow meter, yeah, this thing can go down to 1 gallon a minute. I'm like, well, that's great. I'm dealing with stuff where the maximum feed of this pump is 7 gallons an hour. It would take 1 hour at 100% feed for this to fill a 5-gallon bucket plus, a third of another 5-gallon bucket. So you tell that to Mr. Flow Meter guy, they're like, huh? Oh, I can't go that low. So that's the problem. It's the same thing with flow switches and flow sensors, which on like a lot of your big water moving pumps will have something like that. So maybe on a service pump or a well pump or something, they'll have some type of flow switch. The PLC guys always like that. They get a confirmation that the pump's running, but it's actually based on flow. It's not just based on the motor turned on, the pump says I'm running. They can just it's basically just like a paddle, right? On a pump like that thing over there, they could put a saddle on top of that pipe, stick down a Joe Flem's paddle switch, which is basically just a paddle sitting there. Pump turns on, water starts flowing. It bends the paddle like this. The switch says, yeah, I'm flowing. Same thing. You can't fit a paddle switch in there. There's people that make little teeny, they'll thread right into a 1/4-inch thing. I could put a T in here. I could put this little thing that supposedly can sense flow. But same thing, you talk to those guys. Oh, can this thing sense 0.12 feet per second velocity? They're like, dude, are you crazy? The lowest it can go is like 4 feet per second. So the problem we get into with chemical metering is everything is so small and the flows are so low, it's really tough. Your bigger plant that has bigger pumps, you have a lot more options. It's funny, but it's sad. For these little pumps, the flow switches and the flow meters we need would probably be a lot more exotic and a lot more expensive than one of your plants with bigger motor-driven pumps that are feeding a lot higher. So sadly, there's nothing we can do there. What you can do on, well, let me get a little of the general, and we're going to be back again because like right now the PLC system hasn't been rung out here yet, so we haven't even confirmed. We know it works on our end. Our systems are all pre-tested at our shop before they come out, so we've ran these things with water at our shop to make sure there's no leaks. We've ran all the pumps. We've simulated every signal coming from the PLC to our system. We've monitored every signal coming out. We know our end works. They haven't done the PLC side yet for me to be able to show you the automatic, but I can show you the manual. And one thing I always like to point out to everybody, the way we set our systems up, and I'm the same way, I've been guilty of this myself. This is it probably goes to operators and maintenance, but more to maintenance guys. But I like everybody to get in the habit when they're working with one of our skids and our pumps, that you interface with the pump through the handoff auto switch, not with the local controls. Now right now I have this pump set up in manual, so it'll run on manual. If I turn this pump in hand, you can see it just starts clicking away. So right now the pump's pumping. I turn this off, pump turns off. If I would put this in auto, the pump's not starting because the PLC side's not ready to go yet, but when I put this switch in auto, this pump's waiting for the PLC to tell it, turn on, turn off. So when this switch is in auto, the PLC can control it. Unfortunately, and we'll get into this again when I come back out, they're going to call us back out to ring the signals out, make sure the PLC works. I'm sure we're probably going to be out to do another startup when there's actually chemical in the tank, so we can help get all the settings done. So we'll do more training. But when it's actually capable of running from your PLC, we'll put it in auto, and we can even simulate that to the point that if somebody's in the control room, we can tell them, hey, turn pump 1 on, speed it up, slow it down. We can watch it work. But right now, just to demonstrate my point, this thing's running in manual because I have it programmed to run in manual right now. I've got it running relatively slow. The normal display you're going to see here, it's showing you 60 strokes per minute. There's a little symbol. There's a little symbol next to here. If you look at it real close, it's supposed to actually look like a pump, and then it has a slash and it has minutes. It's showing you strokes per minute. In manual, if I wanted to change that feed rate on these new pumps, I press this click wheel, and you can see it, that box turn black. So now I can just turn this knob to whatever number I want. Hit the knob again, I just change it to 81. This pump can actually go up to 200 strokes a minute. So if you think about that, that's almost 3 strokes a second at max. Super fast. So the pumps have a really good turn down. Usually for startup, I like running them slow. I'm not hurting the pump right now. On this particular side over here, there was something wrong with your tank bolts. They've got new bolts or something coming, but that tank was leaking, so they had to drain the tank to investigate that. There's some new bolts coming, so I wasn't able to use the tank to just sit here and do whatever I want with water. So what I did, and this is what I'm doing now, it's not hurting the pump. We actually just poured water in through here into the calibration column just so I could get all these pumps running. That's what I was doing yesterday. I got all these pumps running. I purged the air out of the system, and I had all 3 pumps on both of your systems running for an hour or 2 yesterday. I'm not feeding anywhere because, number 1, I don't know if they're ready to send anything down this pipe. Number 2, I'd have to keep refilling this column because the tank's not full of water. So right now, I've got the discharge valve closed. It's not hurting this pump. If you look at the column here, what you'll notice is it's bouncing down and it's bouncing right up. So I turned the calibration column into my tank is basically what I did. It's pulling from the column. If I would open this valve and start feeding out to the discharge, instead of that bounce down, bounce up, you would see it bounce down, another bounce down, another bounce down. Every stroke of the diaphragm, you would see it bounce down. So that's a good calibration column drawdown when you see that. And again, we'll go over this when I'm back for startup. We'll do some drawdowns. I'll show you how it works. But this is another kind of quote unquote argument I've gotten into with some engineers over the years. If this is your pressure discussion, yeah, there you go. This is your pressure relief valve, this is your back pressure valve. If you look at them, they look pretty identical, and they pretty much are. I'll show you one here in a second. I could interchange them and switch them. I could buy a back pressure valve and put it where the relief valve goes. I could buy a relief valve, put it where the back pressure goes. It wouldn't matter. What matters is what they're set at, how you adjusted them, and where they are in the piping. So a lot of the really, really old engineering handbooks that have been around forever, they'll show you, again, it's all shown schematically. A pump manufacturer might even have this. It's like, here, recommended installation, and they'll show this little schematic. Here's the pump, here's your tank, you need to have a pulsation dampener, you need to have a pressure relief valve, you need to have this, and almost all of them show the pressure relief valve going back to your tank. So basically, you would have this pressure relief valve. It's here to protect the system, and they would say, send the outlet of the pressure relief valve back to the tank. Well, this is something else that I've done since the first system I built because I don't like that. We tie the pressure relief valve right back to the suction, and we don't tie it into the main suction header. We tie it into the individual suction of the pump it's protecting. And the reason we do that is right like now, troubleshooting. Makes it the whole purpose of a pressure relief valve is what it's doing right now. This valve's shut. Well, more than likely that's not going to happen. Nobody's going to sit here, look at this pump, stand in front of it and shut this valve. These valves are going to be open. But wherever this pipe goes, somebody might be working on something in the plant. They think they're turning off a water line they want to turn off, but they just turned off your feed line and they didn't know it. This is a this is a progressive metering pump. So basically what it means is that you shut that valve off, there's not a safety device here, it will continue to build up as much pressure as it can until something blows apart. Whatever the weakest thing is will blow apart. Usually it's going to be your pump diaphragm, but who knows, it could be a piece of pipe. So basically this device right here, I've got it set at 50 right now. I'm going to be reconfirming the settings once we actually fire things up and I watch how your plant goes, and I'll get into with you guys why I'm picking the numbers I picked. But right now, for starters, at a wastewater plant, my normal numbers would be I'll set the pressure relief around 50 and I'll set the back pressure around 30, maybe somewhere between 20 and 30. So I can easily set this whatever I want. If I take pressure off of this spring, I just brought that down to 40. If I crank it on this spring, I can bring it back up to 50, or I could bring it up to 100 if I wanted to. So this valve allows me to pick a pressure that I never want this pump to exceed. So what I want to look at there, first I want to look at the rating of the pump and everything in your system. We actually, we don't want to pick a number higher than anything's rated for. But again, in a wastewater plant, usually we're going to set the back pressure at around 30, I'll set the pressure relief at 50. The most important thing with these valves, our number one, this is for years and years and years and years, our number one, going to do the cute air quote thing, warranty service call, is improperly adjusted back pressure and pressure relief valves. And I can understand how it happens because it's one of the few things you can touch, especially when the system's in automatic mode. So we've had this problem before where the system's in automatic, and who knows what kind, we talked before about flow pacing and compound loop and all this. Well, a lot of times the PLC guy, he's got his own recipe on what's going to control your pump, and yeah, it's going to take this information, it's going to do this, it's going to be great. They start feeding. Well, if the residual isn't right, most normal people, you can't do a whole lot in the PLC, right? The PLC's doing its thing. It's like, why don't we have enough chlorine? Why don't we have to do something? So there will be a habit to come out here, something's not right, we need to play with these valves. Because it's something you can play with, some people might think, if I mess with these, the pump will feed more. It's like, no, not necessarily. If the PLC is telling this pump to pump at 20, and it really should be 30 right now, nothing you do with these valves will change that. So the most important thing you can do, and again, I'm not going to do it right now, we'll go over it when we come out for startup, but if I would have this at 50, I want my back pressure, which is the setting of this valve. If I opened these valves, this pressure would drop and I could turn the screw under this one and I could set it at whatever pressure I want. I want 20 PSI differential. You kind of want this to be a big flag, and there's two reasons for that. One thing is, these things aren't that highly sensitive, and it's because they just don't need to be for our application. They could make valves like this that are super sensitive, but the valve itself would cost as much as the pump. We don't need that much sensitivity here. So you don't want them too close. I've had one customer, he thought he was doing it because he's going to extend the life of his diaphragm. Because what happens if somebody shuts a valve? I don't want it to go all the way up to 50, even though this pump's rated for 102. He said, so I've had people try to set this at like 20 and set this at 22 or 23. You cannot set them that close. I guarantee you, both of them are partially opening at the same time, and that's the hardest thing to troubleshoot. The pump will pump to the point of least resistance. And if you set these things too close, half your output might be coming out of here, half's just sitting here going in a loop, and that's the hardest thing to troubleshoot. So again, my long-winded thing, why I pipe it to the calibration column the way I do, if this was piped back to your tank, it would be another gray pipe, right? Going up and going overhead and going into the tank. Right now, I can see I got a problem looking at that calibration column. I see it going down, I see it going up. I know, just because of my experience, I know more than likely it's this. If all these valves were open right now, and I knew the valve was open at your discharge point, my first guess would be somebody probably messed around with this. It's not set 20 PSI higher. I would confirm that. If that's not what it is, it could be this needs service. There's dirt in here. It's allowing flow to go by it when it shouldn't. Or it could even be like the pump suction check valve. If the pump suction check valve's not working, that would have this same symptom. But the nice thing is I can see it right now real quick. If this was vented back to your tank the way those old engineering handbooks go right now, that column would be going doink, 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 just like it should be. And I could probably even sit here with my stopwatch and do a calibration column drawdown and go, yeah, that thing's pumping exactly what it should be. It's pumping 3 gallons an hour. That's what it should be feeding right now. What we wouldn't be able to see is, yeah, it's feeding it back to your tank. It's not feeding it out your pipe. So having it in this loop like this lets us have a visual cue. So this is something else I'll throw out there. We never try and get out. We stand behind our stuff. We honor our warranties. Again, the call we have, my pump's not pumping right. I think something's wrong. You got to get out here right away. A lot of times what you're going to have, almost every time, and it is not us trying to get out of making a warranty service call, but you got to realize we're 3 hours away, and it might be something very simple that we can resolve real quickly over the phone, and you might learn something. And a prime example of that is, again, I can't tell you how many times we've sent a service tech 4 hours across the state that comes back and says, yeah, somebody had the pressure relief valve adjusted wrong. Took me 2 seconds to fix it, but he had to drive 4 hours to go over there and do it. And again, not that we're against that, but every one of our skids has this sticker somewhere on it. This is your serial number. The number after the dash is the most important thing. This one says 2005. So if you call our shop, you're probably not going to get me. You're going to get somebody, and we've got customers all over. We don't even remember what we're talking about. But yeah, I'm up here at the Northwest facility. We're having a problem with the pump. I need somebody up here right away. They're probably going to say, hey, if you have this information before you call them, better. But if you don't, they're going to say, hey, do me a favor, run out, look at the skid serial number, call me back. When you give them that number, they go to our job file at the shop. They've got everything. They know the exact model of pump you have. They've got all the CAD drawings, the way this thing was built. They got the electrical control panels. They've got everything. So then they're probably going to say, all right, what's going on? Well, we're not pumping anything. We need you out here right now. If they say, hey, do me a favor, they'll talk you through this. You got a calibration column on your skid, right? I want you to do something for me. They're going to talk you through. Here's how we fill the calibration column up. Switch the valves. We're going to watch the calibration column. Again, they're not trying to get out of coming out here. They're trying to help you as quick as you can. And you'll try something, and they'll say, okay, do me a favor. Tell me what the pressure gauge reads. Tell me what your column's doing. Well, the pressure gauge is doing this, and the column's kinda. And they'll say, okay, do me a favor. There's a valve labeled chemical discharge. Just close that valve and stare at the pressure gauge. Tell me what happens. All right, yeah, I'm staring at the gauge, and it's kinda, I think it went up a little, but it's kinda staying the same. And they might say, do me a favor. There's a pressure relief valve. They're going to talk you into where it's at. You say, get yourself a screwdriver, take the cap off, and tighten that thing like a turn, and watch your gauge and see what happens. And you might say, oh, yeah, it just came up. You're going to say, okay, well, do it again. Let's set it for 55. Okay, cool. Then they'll tell you, open the valve back up, do a cal column test. Boom, you might find, holy cow, I just got the system up and running. So we got you up and running fast, and at the same time, you got to learn something by actually seeing it. Because I get up here and I tell, I say all this stuff and it doesn't make sense. When you actually play with it yourself, you'll get better understanding. So the whole point in that long dialogue there was that if we're asking you to come out and do a few things, we're not trying to get out a warranty. We will send a guy up here as quick as we possibly can if we need to send somebody up here, but we're honestly trying to get you back up and running as fast as we can, which might be, again, a very simple thing. So going all the way back to where I started talking about my switch, if I'm the service guy, I'm probably sitting on a 5-gallon bucket, or I'm doing something down here and I'm actually working on this pump, and I might have made some adjustments. I made a repair on the pump. I had to shut it down. Well, after I'm done, I want to turn it back on because I want to do a calibration column drawdown. I want to make sure I think the pump's doing what it should do. So I'm a smart guy. I'll get lazy and I'll learn that, hey, I got to get up off my bucket, turn this off. Now I got to get back down here and do this. Now I got to get back off my bucket and I got to turn this on again. I'm going to learn that, hey, I don't have to do that. I can push this stop button right here. I can sit on my bucket and I can do this, and I can turn the pump back on, and I can do a drawdown. I can do my stopwatch, and that's perfect. You can do that. But what you have to realize is that when you do this, and this isn't unique with Prominent, pretty much every single metering pump I'm aware of that's microprocessor controlled, and every VFD that you have running around here, although a lot of them are buried inside a big stainless cabinet, almost all of them will have a local start-stop button on the front of the VFD, and pretty much almost all of them will override everything else. They'll override, it's kind of, I think it's a liability issue. It's like an e-stop, right? Because from the manufacturer's perspective, They have no idea that this panel is right here mounted beside this pump, and there's an on-off switch. This panel could be way over there. This panel could be nowhere. This pump could be controlled by the Oracle on the other side of town. And somebody's standing right here in front of this skid, and there's chemical spraying everywhere, and they run up and they hit this stop button because the PLC thinks, yeah, feed, feed, feed. But the guy right here is like, no, turn off. So this is a safety feature. But you got to be careful when you do that, because right now, like I say, this thing won't run in hand, right? Because I shut it off there. Well, guess what? It also won't run in auto. I think I did a good job. I repaired the pump. I did my calibration call down. I'm ready to go home and drink a beer at my dog. I grab my tools, I throw it in the truck, and I drive away, and then I get that beeper call at 2:30 in the morning going, that freaking pump you worked on isn't working, what's going on? And you come out here and you realize, oh my God, I forgot to push this button on the pump. Because if I push the button again, now the pump comes on. So the button on that pump right there will override everything else. So what I tell everybody to do, I'm still not against it. Again, I do it when I'm working on a skid because I'm sitting down there in my bucket and I'm doing my things. So there's a couple things that you can watch for. If I push this stop button with this in hand, there's a little symbol over here on the left, and these displays are so small, but there's a little symbol. It looks just like this. It's a hand with a finger sticking out. It's a symbol on this pump telling you somebody pushed this stop button. I'm stopped. I'm stopped locally. If I turn that on, that symbol goes away. If I turn this switch here to off, in the same place where that hand was, there's the two bars, like the universal pause symbol, like on your cell phone or whatever. You got the two bars for pause, you got the triangle for start. It's showing a pause signal right now. That's this pump telling you something remotely. It doesn't know it's this switch. It could be the PLC. It's the pump telling you this cable right here is telling me to stop. So could be the PLC, could be the switch. They're both coming through that same cable to go to the pump. If I do both, even though the pump wasn't running, and that's the scary thing, even though this pump wasn't running, I just pushed that one time, and if you look right now, it's actually toggling in between the two bars and the hand with the finger, the two bars and the hand with the finger. It's basically telling you, somebody told me to stop here, and somebody told me to stop here. And guess what? If this guy says, all right, turn on again, it doesn't care, because the other guy still told me to stop. So what I tell everybody to do is, if you're out here interacting with this system, and you've done anything, you've been doing calibration column drawdowns, you've been messing with valve adjustments, anything you do, when you're getting ready to go to your truck or go to your office and leave, last thing I always do, I turn that switch, yeah, pump turned on. I turn it off, I'm not touching nothing, I'm out of here. If you want to go a step further, when your plant's up and running and it's in auto, if I was the maintenance guy, auto, I'd be calling on my radio up to the office. Hey Joe, I'm out here, I just finished working on pump 3. Can you do me a favor? Can you turn it on real quick? Boom, I heard it turned on. Yeah, speed it up a little, slow it down. All right, cool, put it back the way you want it, we're good to go. Walk away. You know that everything worked, you just worked through your guy in the control room, you know that the system can control it. So any questions on that?
The stroke on that part there, high.
The stroke, it's pretty tricky, so good question. So on your motor-driven pumps, you got like a big mechanical knob, right? On this one, you got this knob, but it doesn't do anything. Well, one thing you're going to notice, and this will confuse some people, and it confuses me too, but if you just turn this knob without pushing it, right now it's showing the strokes per minute, like I said. That's personally, to me, that's where I like leaving these set at. You know how fast the pump's running. And again, if I push this knob, it turns it black, and I can change that 55 to 60 strokes a minute. Push the knob again. If I don't push the knob and I just turn it, you'll see the display changes. Now it's showing me 100%. What the heck does that mean? If I turn it again, it's actually showing me the time. If I turn it again, it's showing me liters per hour. And if I turn it again, I'm back to my strokes per minute. So you're not hurting the pump. That's just what information it's showing you. So if you come out here and you see this, it's like, oh my God, my strokes per minute's gone. I got this weird ass number. It looks like the time of day. It's like, just don't push the knob, just turn the knob and you'll get your strokes per minute back. Now to set the stroke length on this pump, it's done electronically.
Okay.
Turn this until you see this percent. That's 100%. That's 100%
okay.
stroke length.
Okay.
Same deal. If I
Okay.
push this, it makes that black. I can crank this thing down, push the button. I've just changed the stroke length to 74%.
Okay.
And that's where I was getting into earlier, how I think it's pretty cool with these pumps that it adjusts the output to the PLC. If somebody did that, you basically just cut the capacity of this pump down 75%. It's no longer a 7-gallon-an-hour pump. It's a 5.5 or whatever that works out to be. So most pumps, the PLC would know that. With this pump, the PLC is going to know. If I had my electrical meter hooked up to the milliamp output before I did that, it would have been sitting here showing us a number. Who knows? It might have been 10 milliamps. As soon as I changed that to 74 and hit it, you would have seen that 10 milliamps drop to 8.2 or something. It would be this pump telling the PLC, hey, somebody just slowed me down. I'm not feeding what you thought I was feeding before. So typically, for every chemical, you're better off at 100% on the stroke length. And the reason is because, get that back to 60. The reason is because this is, I like using these big ones, they're just easier to understand. This is a diaphragm pump. It's no different than this. This one's just a lot bigger. But basically inside this head, when we're looking at this strokes per minute, this 60 number, we're talking how many times a minute is this diaphragm going back and forth? 60 strokes a minute is 60 times. I'm going back and forth 60 times, and going back and forth 100 times, and going back and forth 10 times. The strokes per minute is how many times per minute is this diaphragm moving back and forth. The stroke length, the percentage, how far am I going back and forth? I'm going 100% back and forth, or I'm going 50% back and forth, or I'm going 10% back and forth. So you're playing with two different things to get this pump to work for you. How far back and forth does diaphragm move? How fast does it move? The operating concept of any diaphragm pump is very, very simple. And basically what you have is check valve. Your check valves are obviously a lot smaller, but it's the same exact thing. All the check valve is, let's see if I can get, this should be loosely assembled. All this white stuff is just holding it together and really isn't even important at all. It all comes down to this. It's nothing but, in most cases, a round ball, exactly like this, and that round ball is either sitting on a hard seat like this one is. This seat's tapered. It matches the curvature of the ball. Some pumps, some of your smaller ones, it's actually just seating on a rubber O-ring. But that is the only thing that makes this pump work. You've got the same exact identical check valve on the bottom of the pump head and on the top of the pump head. They're identical and they're interchangeable. We could take, on Prominent, they put arrows on them. Our guys blacken them out with a Sharpie so you can see them. I could take these valves out, swap them, the pump would work fine, as long as the arrow's going the right way. The arrow always points from the bottom of the pump to the top of the pump. So what happens is this diaphragm comes back. It's actually creating a negative pressure in a pump head. It's making a vacuum. The diaphragm's coming back. It's trying to implode the pump head. It's pulling in on the pump head. Oh, there goes my ball. So this probably wouldn't pump very good anymore because it's got sand on it. So it's pulling a vacuum. It's trying to implode your pump head. It's trying to get something into the pump head. So what happens is this ball's on the bottom of the diaphragm. This vacuum comes in. That vacuum's strong enough, it lifts this ball up. As soon as this ball lifts up, it's actually pulling chemical from the piping into the pump head. The millisecond this diaphragm stops at the back and starts coming forward, it's now creating a positive pressure. Again, in that backward stroke, it came back, it made a vacuum, it lifted this bottom ball up. Your top ball's sitting up here, the diaphragm's below it. The vacuum's actually sucking that ball even harder against the seat, right? So it's not pulling anything in from the discharge side. This ball is sitting here, slammed against the seat, and this vacuum on the bottom of it's actually pulling it even tighter against the seat. So the second that diaphragm starts coming forward, it slams this bottom valve shut against the seat. Now it's putting positive pressure on the pump. It's trying to blow the head apart, explode it, but the top check valve, the ball lifts up. So all the liquid that just came into the head from the bottom valve opening is going out the head from the top valve. So That's the simple operating concept right there. It's just check valves in these pumps. Every time that diaphragm goes back, this ball lifts on the bottom, it comes forward, it shuts. Opposite on the top one. Every time the diaphragm goes forward, ball lifts up, chemical leaves ahead, diaphragm starts going backwards, it shuts. So when, and I say when because these modern pumps are so good, most of the time when there's issues with our system, it's something to do with the valves, unless the pumps have been running for years and years and years. When it does boil down to, yeah, it's the pump itself, something's wrong with the pump, these diaphragms are built so well, and they do wear out. They can last a long, long time. Usually it's just service to the check valves, and a lot of time it's as simple as just flushing it with water, and a lot of times you don't even have to take it apart. You could actually leave the check valve assembled, take it to a hose or a sink or some water, just flush it with water, but the way you saw it, it's just a ball sitting on an O-ring or a ball on a seat. Even just some dirt or grains of sand, like I just dropped that ball, right? It's sitting on that seat. It's supposed to seal, but now there's little salt crystals or sand, so the ball's not totally sealed 100%. So your pump's probably still working, but it's allowing a little bit of chemical to bleed in and out the wrong direction, right? If your top check valve has dirt on it, well now, when your diaphragm goes backwards, it's wanting to lift the bottom ball up. It can also suck some of the chemical from the top too, because that ball's not totally seated. So that's when you start noticing things like, it's kind of letting you know where it's like, yeah, you know, I used to do a drawdown on this pump at 100%, and it was about 7.5 gallons an hour, but now I do it, it's more like 6.8. Well, that's not horrible, but that's probably telling you, yeah, you're probably still feeding good enough for now, but more than likely, you're starting to get a little bit of an accumulation on the balls in your check valves. Your pump's not feeding quite as good as it used to. That same accumulation can be accumulating on the diaphragms in your relief valves. And now, even though they were set right, and you understand what they do, they've got some dirt and accumulation in them where, yeah, even though they're set right, they're allowing a little bit of stuff to bleed by them. So usually that's all it boils down to, is you're just getting a little bit of dirt and sediment and build up on the check valves.
Can those be cleaned with a little boracic acid and water?
Yeah, they could. In a lot of cases, even just water. But yeah, like for bleach specifically, uric acid, or if you don't want to do anything that aggressive, distilled white vinegar. It just takes longer. What happens with sodium hypochlorite is you'll actually get like a crusty scale buildup. You've probably seen it at your injection points. So muriatic acid, just the mild acid like you buy at a pool store, if you put your parts in there, you'll see it start fizzing up immediately, and in like 30 seconds it's gone and everything's clean. You can do the same thing and not have to mess with acid with distilled white vinegar. It's just not going to be immediate. You could put it in distilled white vinegar, leave it overnight. When you come in the morning, same thing. It's going to be perfectly clean, and you're not having to mess with acid. But again, I get off tangent sometimes. Where I thought that was the stroke length. When I'm sitting here doing this, showing you guys diaphragms going in and out, I am greatly, greatly, greatly exaggerating how far this diaphragm moves. I bet if we took the head off of this, if we take the head off of this pump, there's a shaft sticking out of the pump, and that's what this diaphragm screws on. So that shaft's going in and out pushing this. If we took the head of this pump off, unscrewed this diaphragm, and put a tape measure next to that shaft and turned it on at 100%, I bet you that shaft's only moving this far. That's at 100%. So it's only moving this far. And we want it to operate these check valves and do that. And then we're going to go up and say, hey, I don't want it 100% anymore. I'm going to change it to 50%. Well, now that diaphragm's moving like this. And we're asking that diaphragm to move only this much and lift these check valves and feed chemicals. So they can do it. That's why the stroke length is there. But typically, you're going to get better performance leaving your stroke length at 100%, because that's going to allow the diaphragm to travel the farthest to bring the largest volume of chemical inside the head. That's another thing to discuss just quickly to do with hypochlorite, not these systems, but the same operating principle that I just talked about. The check valves in the head, it relies on the fact that liquids are non-compressible, okay? So that means the head needs to be 100% liquid full for that to work. If the head is 100% liquid full, when it moves backwards, it's pulling that vacuum on whatever liquid's in the head, which is transmitted to everything else. It's trying to open a check valve or do something. When it comes forward, same thing. It's pushing on that water, that chemical, and it's pushing that force out, and that force is opening the top check valve. It's not that one little air bubble or gas bubble is going to shut one of these pumps down, and it always sounds funny when I say this, but I guarantee you every sodium hypochlorite metering skid I have out in the field is passing gas constantly. If you look at a sight glass on a sodium hypochlorite tank, there's little like beer bubbles in it. They're always there. It can feed a little bit of that. It's not a problem. But if you've ever heard the term vapor locking on a chemical metering pump, that's what can happen on sodium hypochlorite systems. And again, it's not any little gas bubble gets you, but over time, gas bubbles are building up in your piping. If I could make, I considered making a skid out of all clear piping at one point in time and putting it in the plant right down the road from my shop just to study gassing. But I went against it because I'm like, I would have to have the right person there, because I would have people calling me constantly, even though the pumps are running and the residual's fine, but they would say, this pump's gassed, it's vapor locked, you need to get out here right away. Because what we would see, every single fitting that you have, there's a high spot in the middle here, no matter what we do, right? This 45 degree has a couple butts in it to where it stops the piping. When the piping's glued in, there's a section right here that's a little higher than that. So basically, there is a spot in every single fitting in this piping where gas can collect on the top of that fitting, because the inside of your pipe, you know, the inside of your pipe here, the inside of your pipe's here, but the middle section of that T is this tall. So in that little bitty section right there, all these little gas bubbles can go, oh, I'm happy, I'm gonna stay here. So over time and over time and over time, every single one of these fittings is collecting a little bit of gas, which is getting bigger over time. What can happen, after enough time, it gets big enough where all of a sudden, it gets pushed out. So now it's coming down the pipe, coming towards the skid. Well, that's what can happen, is if all of a sudden this pump makes one of those strokes and it lifts that bottom check valve up and it's wanting to bring chemical in, blink, it gets that big gas bubble in. And now it goes forward. The gas bubble or air bubble acts like a balloon. The liquid's not compressible, right? The diaphragm comes forward, it's pushing check valves. You get this gas bubble in here, the diaphragm comes forward, it's like a balloon. The gas bubble goes like this, no check valves move. Diaphragm goes backwards, gas bubble goes like this, no check valves move. So the pump's running, you're not gonna hurt these pumps, they can run dry, but it's sitting here going click, 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 click. It's like, I am not feeding, what the heck's going on? There's a gas bubble in that pump head that's just sitting here doing this and doing this and doing this, and you're not feeding chemical.
Oh, it's gonna make that noise?
Well, usually they get louder. When the pumps are liquid full, they get pretty quiet because the liquid actually muffles the sound of the check valves. When you get air in there, you'll hear them clacking a little bit louder. On these pumps, it's pretty easy on our skids to do it regardless of what kind of pumps you have. On these little pumps, a really nice feature is most of them have this bleed valve right here. So if you look at this, we have this ran with flexible tubing right to your calibration column. And the nice thing is if you look at the pump, the bubble's gonna go to the top, right? That's where it's gonna be. That's what happens, is the bubble comes into the pump head and it basically goes all the way to the top and it's sitting right here under this discharge check valve. And it's just doing that compression thing. It's not letting your check valves work. On this pump head right here, if you look at where this star-shaped knob is, it's at the very top of the pump head. They've got a little micro port drilled immediately right underneath the check valve, right where that air bubble is. So on this kind of pump here, if I thought it was vapor locked, I wanted to clear the air bubble. Right now, this pump is feeding. The pressure is going to start building up. If I come over here and I crack this star wheel, you're seeing it come here, and you can even see on this tubing right here. If there was a big air or gas bubble in this pump head, I might come out here and the pump's making a really loud noise. Clack, clack, clack. I think this pump's vapor locked. I would crack this valve open. You might hear it kind of clack, a little quiet clack, and you would look at this tubing and you'd see, oh yeah, air bubble, air bubble, air bubble. And all of a sudden the pump would get kind of quiet and you'd see it start to be just liquid. And once you see that, you just cleared the air out of this pump head, you close this valve, you should be good to go. On our systems that don't have these, they only put these valves on these smaller pumps. At your other plant, you've got the motor-driven pumps. They don't have that valve built into the head. It's a little more of a pain, but you can use our flushing outlet, like I said before. You can either, we angle them out now, so you could either just take this bottom union nut off right here and get yourself a little container, or you can put a barb fitting in here, get yourself some hose so you can put it in a 5-gallon bucket. But same exact thing. if I would crack this valve open, that's a 0 back pressure point to go. Your tank's full of chemical. We've got all that head pressure in there. As soon as we would open this valve and this pressure would drop to 0, you'd see we'd be pushing all the air and gas out of all the piping. It usually takes just a second. If the pump's vapor locked, I got a container I can put here, open that valve for 1 second and shut it, and right away your pump's running again. Once, the only place the air bubble is a problem is in the pump head. These little bubbles that are in the suction side, like I said, they're not hurting you. The chemical's flowing past them. It's not until it gets put into your pump head. Same thing. Oh, I used your flushing outlet, but what if I got an air bubble here? It's not going to hurt us. It's not going to shut us down. Even if there's an air bubble trapped in here, which there probably is, this high section of the piping, it's going to push the chemical past that air bubble and out your piping, and your residual is going to show you that. I had a customer think it was crazy because he installed a pump by himself on a shelf. It was all hooked up with tubing and everything. And he was like, I don't understand what's going on here. He had a piece of tubing coming off the top of his pump, and it looped up like this and went down, and it connected to some piping, and it went that way. So his pump was feeding fine, but in the top of his tubing, right at the curve, there was like an air bubble this big, and it's moving back and forth. And over time, that air bubble would grow. And he's like, I don't think I'm pumping. You need to get up here. And of course, I'm trying to tell him, man, you really need to get a skid. So we got a Calcom. We can tell what the hell we're doing. You got a pump and tubing. But he's like, I'm not pumping, man. Look, I'm vapor locked. And I said, well, what's your residual right now? Oh, it's 2.5 parts per million. I'm like, well, then you're pumping. So you had to look real close. It was kind of like that opaque, white, translucent tubing. But yeah, there was a big, giant airspace in it, this big, going like this. But if you went up, you really stared at it, there's a little trickle of bleach running along the bottom that's going right past that air. So the pump was still pushing the chemical out the pipe. So again, the point there is the air bubble is only going to hurt you in the pump head. And if that's what got you, if it's vapor locking, if you got this bleed valve, I mean literally 2 seconds, you open this bleed valve, you're going to see a bunch of air coming out the tubing, the pump's going to make some racket, it's finally going to quiet down, you close that valve, you're done. You just degas the pump head. On our other systems, use this valve. And usually what I'll do when I use this valve is I'll shut the pump down for a second, because you don't even need the pump to help you. Because again, we've got gravity from your tank right over here. If this tank is this full of chemical, even with this pump shut off, as long as my valves are open, all I got to do is open this valve, and the head pressure from that tank is going to push everything, out of the pipe. Okay. Any other? I'll go over one other. And again, we'll go over this again. Your back pressure valve, like I said, same thing. It's got a screw in it. And what I always tell everybody, and when I come back for startup, we're going to do this again when all the pipings are open, and I'm going to show you. And this is the thing my guys will tell you over the phone. If all our valves were open and we were feeding right now, this is going to be at a number. I'm not sure what your final number is going to be yet until we do startup, but it's probably going to be somewhere around 20 to 30 range. When you shut this valve, if all these valves were open again, it would be at like whatever I set this valve to, maybe 30. If this system was running and it was at the roughly 30 I said, and I shut this valve, what I want to see is the second I shut that valve, every stroke of the diaphragm, blink, I'm seeing this thing start to climb, and it climbs up a good 20 more. If I shut this valve, and it hardly climbs at all, and it only goes up a couple PSI, or it's taking forever to climb, I'm going to pull this out and go, it's like, oh yeah, there we go. We want that big differential. This is a worst case scenario safety device. We want it turned off, not doing anything, unless somebody closed the valve. So we don't want to have it too close.
So you want each at about 50 and then 20 with them both open?
No, I want them, well yeah, this one you're not going to know, but yeah, with this valve closed, I want it at my higher pressure. With this valve open, it's going to come down and read this pressure. So if this was open and that's why you can only, and again, that's why we install them where we install them, you can only tell what this is set at or what your adjustment is when this valve is closed. So like let's say I had my numbers that I kind of like for wastewater plants, 30, 50. If this valve was open, we'd be at roughly 30. I could take this knob off and I could start screwing this wherever I want, and I'm not going to see what the adjustment is. Because it's only going to tell me what that adjustment is when I close this valve. Unless I start unscrewing it and I make it less than my back pressure. If I've got this set at 30 and I start cranking this back, I start getting below 30, all of a sudden you're going to see your pressure dropping, because it's just like, oh, I just told it I want it to go up. You know, the pump's going to take the path of least resistance. That's what it boils down to. So that's why this is the pipe going out to your injection point. You want this to be the path of least resistance. If you make this the path of least resistance, or if you make it so close they're almost identical, it's going to be putting some both places. So that's why I tell everybody, don't keep them close. Go for 20 psi differential. That way you know. And the other thing that you can remember, and again, it's not hypercritical. It really isn't. Your pressure relief, whatever I set it at, it's going to pretty much stay the same if I set it at 50, whether this pump's running at 100% or 20%. It might take it longer at 20% to build up to that point and finally get there, but it's going to come to that same number because we're deadheading the pump. Once we get to that number, the pump is deadheaded. When we set your back pressure, like I said, I'm going to do roughly 30. That number's not always going to be 30. That number's going to be dependent on the flow. When the pump's running 100% wide open, it might be 30. In the wee hours of the night, if this pump gets turned way down, that 30 might go down, it's only like 26 or 24 or something. That's okay. And that could be another reason why sometimes these get out of whack. It's because somebody comes by here at night, it's like, wow, that back pressure's down to like only 22. It's supposed to be 30. And they'll crank it up to 30. Well, they just cranked it up to 30 when the pump's running at a really, really low rate. And then the next morning and the flows pick up and everything speeds up. Now all of a sudden we're up at 37 or 38. So it doesn't need to be dead nuts on 30, and it doesn't need to be 30 all the time. It's the thing that over time you're going to get used to on your skid. It's going to be second nature to you, depending on your shift and your time of day and the time of year and Taurus and all that crap. You guys are going to know, yeah, these things are usually running around somewhere between 50 and 60 on the display. That's going to be something you're just used to in your head. You walk by here, yeah, that looks good. You're going to be used to, yeah, that's usually somewhere over there near 20 or 30. Blah. The red flag is you glance by your skid and you see a needle way up. You're like, whoa, what the heck's going on? Why is that needle at 50? Then, you know, is there a valve shut? Did somebody shut a valve in the discharge? Has somebody been playing with these? Do I need to reset them? So again, we'll go over it. We'll go over it at startup when everything's running, we're feeding chemical, and we'll do some tests to show you how that works. Just another thing real quick. I've had some people say, you know, hey, we're at a wastewater plant here and we're discharging into open atmosphere. And again, some of these guys thinking maybe they're going to save money. You know, I want my diaphragms to last as long as they can. Why set the back pressure at 30 and have this diaphragm have to push 30? We're feeding into zero back pressure. Can't we set this at almost 0 or only 5 or something like that? Well, two reasons you don't want to do that. Number one, it also acts like an anti-siphon valve. So we have to have it set at a high enough pressure where it will override the pressure generated from your tank. Every 2.31 feet, you get 1 psi. So if that tank was full, we might have, you know, who knows what, 5 psi of pressure coming into this system. If we didn't have this valve here at all, there's no springs in these check valves, like I said. If we didn't have this at all, that tank would flow right through this system, right through this pipe, and just spill the whole tank full of bleach wherever it's going. So we need to have enough back pressure to stop that from happening. So that's one function of this. The other function is to help the check valve. Some people might find it surprising, but a lot of pump manufacturers in their specifications, they'll have a spec for minimum recommended back pressure. And for most pumps, it's 20 to 30. And it's because, again, that there's no springs in here to help this check valve seat. It's basically just gravity making this check valve seat. But having some back pressure, having 20 to 30 psi on the discharge side of that pump, that 20 to 30 psi is your spring. That's pushing against this check valve, and it's making this check valve slam shut against this seat until the diaphragm comes forward and makes more than that 30 psi to send the chemical out. So the back pressure is actually your spring, and it's helping you pump. So typically 20 to 30 is the minimum that I want to set back pressure valves for, because, you know, we want to make, it's all about pumping and keeping your pump happy, so we want your check valves to be reliable for you. One more quickie, and then I'll let you guys get back to your warm office. This is called a pulsation dampener, and what its job is, These pumps are fairly smooth. To show you how good of a job it's doing, basically what I would have to do is either take this off and put a plug here, or if I overfilled it with air, it would simulate it not being here at all. But especially at max speed, just for the heck of it, we're gonna crank this baby all the way up to 200 strokes a minute. So that baby's pumping away. I'm gonna have to go back and see if I put my stroke length back too. I'm not sure. So let's check that real quick. Yep, I'm back at 100. Okay, so if you look at that gauge right now, that gauge is bouncing for sure, right? It's deflecting a little bit, it's bouncing. But if you look at it real close, I mean, it's not even quite 2 PSI, it's like 1 PSI, and it's pretty soft, right? I mean, it's going back and forth, but it's not like bling, bling, bling. It's kind of just nice and soft and gentle. That's all because of this right here. These pumps are generally called electronic pumps. These little pumps in a box compared to what your other plant has a motor on it. These little teeny pump in a box are kind of called generically electronic pumps or solenoid pumps, because that's what they are. There's a solenoid in here. On your motor driven pumps, you got your motor up top, right? There's a big gearbox on the bottom. The motor's turning those gears are turning the pump shaft, and that pump shaft, if you plot a motor driven metering pump's chemical profile out on a curve, it draws like a curved line. You've got your discharge stroke, you've got your suction stroke, but it's just like this. It's a sine wave because you got this reciprocating gear and your diaphragm's always going like this and going like this. These little pumps, when you hear that click, 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 it's an electronic solenoid. It's just like your key fob on your remote control for your car. It makes your door locks go up and down. It's an instant on. It's not a motor turning a gearbox going this and this. It's click. So every time this pump runs, that solenoid is going slam as fast as it can all the way to the back. It's not a smooth motor going like this. It slams all the way to the back. They de-energize the coil, and it's a big giant heavy spring that none of us could compress that pushes the diaphragm back forward. So when you plot these out on a curve, it's this. Doink, 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 doink. It's on or off. There's nothing smooth. So without one of these installed, either one of those, a motor driven or one of these, you're not going to have this little 2 or 1 PSI like I had, nice and smooth. You're going to have a with a motor driven, even though the pump's bigger, it's not going to be as bad as this. If I didn't have this dampener here, if it wasn't properly charged and we just did what we did, that gauge would probably be bouncing back and forth 5 PSI, could even be 10. It'd be like this. And if I asked somebody, hey, what pressure do I have? It'd be like, 52, I'm going to call it, because it looks like it's bouncing between 50 and 60. So it's a real simple device. It's got one wear part in it, which is the bladder. The bladder also acts as the gasket. The outer area of it is kind of molded in like an O-ring form. It sits in this groove. But all this thing does, it's called a rolling bladder design. So the way these work, and this is another one where the air charge isn't that critical. It's going to change over time because the air is actually going to slowly migrate right through the bladder. So eventually the pressure might need to be revisited. But in most cases, these things work fine until it's time to service the skid a year or two later anyway. Your indication is your gauge. If you guys come by here and your system's running, whatever feed rate it's running at, and your pressure's in the ballpark, our pressure's usually somewhere 20 to 30-ish. If you see your pressure 20 to 30-ish and the gauge is doing this, you don't need to recheck your air pressure. It doesn't need to be perfect. It's doing its job. It's only if, it's in the 20 to 30 range. That's our normal, but man, that thing's freaking bouncing all over. It might be like, you know what? Maybe this bladder ruptured, or maybe all the air's finally disintegrated out of it where it's not doing anything. Because theoretically, you want this set for ideal performance 2 PSI less than your back pressure. It's pretty much the same thing as a residential bladder tank. If any of you guys have wells like I have for a house, 2 PSI below your back pressure. So if your back pressure is 30, in an ideal perfect world, you have this set at 28. As long as it's less, it's doing its job. And again, I don't like them being that close because, like I said, we're trying to set your back pressure at 30, but depending on your feed rates, it could bounce around between 25 or 30, which is fine. So I'll usually have this set about 10 PSI less, which is fine. So basically what we have is we have an air charge in here. And that quick shot, bang, that comes out of that pump, it comes up into here and it rolls this thing up, and as it's rolling up, it kind of slows down. It's like a shock absorber. It's called a pulsation dampener. That heavy bam that would come and deflect this gauge and make it do this comes up here. This thing takes it, absorbs a hit, and relaxes. And the next one comes, it absorbs a hit and relaxes. It absorbs a hit and relaxes. So that's why this pressure has to be lower than your back pressure. If our back pressure was 30, we had this aired up to 35. We put more pressure than the back pressure. We basically slammed this thing all the way to the bottom and sealed this hole and turned it off. And we made it like it's not even there at all. It's not effective. So that's all it does. And again, you don't need to revisit it all the time. You look at this gauge, and if that needle's just gently fluctuating back and forth, you don't have to worry about your dampener. Even if it's down to only 5 psi, it's doing its job. Even with 0 psi, they'll do their job. You might just be using more of it, but if your gauge is nice and smooth and steady, you know that this thing's working regardless what the pressure is. The other thing that's kind of funny with them, I aired these things up to roughly about 20. But right now you'll see it's over 20. They'll equalize with the system pressure. If I turn this pump back on, this gauge is going to climb, this gauge is going to climb. The only time you can actually tell what your charge is in these dampeners is with the system totally shut down and all the pressure bled off your system. So in other words, like when I'm holding it in my hand, pressurize it. That's when I know what the charge pressure is on this. Because once we're up and running, this thing's going to equalize the system pressure. You're not going to know, because what's happened is as it's running, this diaphragm has found an equilibrium in the middle, and it's kind of hovering here doing its job, so the pressure equalized. So you can only tell you can only tell what this pressure. If I wanted to know what this pressure was on a system and I'm out here servicing it, I would shut your whole system off. I would close the valves. I would put my little bucket here. I would open this drain valve. I'd blow all the chemical out, and I'd get this gauge down to 0. And then I'd be looking at this, and that would tell me, do I have air in here, and how much air do I have in here? That's the only time you're going to know when your system's running. You can't tell. That could have too much air in it, could have not enough air in it. There's no way we can tell. But again, I can tell by that. I don't care what it is. I don't care if it's got only 2 psi or if it's got 20 psi. I see that and I'm happy. It's doing its job. Because that's another thing. PVC and CPVC are very brittle materials, right? We all know that. They're not good for impact resistance. We hit this thing with a hammer, it's going to shatter. So a lot of people don't think about it, and sometimes it is workmanship, but you might have somebody, they either build you a skid like this or they just do some field plumbing, whatever. But years later, there's things cracking and there's leaking. And like, let's say it's one of these chemical metering pumps, and all of a sudden this body cracks and this cracks, and somebody might say, man, whoever built that, freaking heavy-fisted, they don't know what they're doing, they over-tighten their joints, too much Teflon tape, whatever. That's possible, that could be. But what it could also be, if this dampener wasn't here, and this gauge was like ding, 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 well, again, that's a high frequency shock wave. That, just like we said, this is a square profile curve. It's bow, bow, bow. Water hammer, you guys have probably heard about it. I was doing a job at the Space Center one time. That's where our shop's at. We're in Brevard County. I was doing a job at the Space Center. They had a huge elevated water tower out there. I think it was 125 feet or something up in the air. And there's a little well house system or a pump system underneath it. They were doing this rehab job. There was a chemical feed system in there. I was there to start up the chemical feed system. There were transfer pumps. So it was go time. Everybody's getting ready. You ready? Yeah, I'm ready. I'm ready. So I'm in this little room off to the side next to my equipment, and I hear wee, I hear pumps turning on, I hear stuff happening. My skid turns on, everything's going good. I'm cool with everything. Gets to the end of the cycle, that tank gets filled, and all of a sudden I just hear freaking noise and people yelling and bam, and just people running out of the room. It's like, what the F just happened, man? Go into the other room, everything settles down. It was probably like 16 inch. There was 16-inch piping knee high off the floor going to these pumps with big concrete saddles and straps that held it there. Concrete was all over the floor. All the straps were broken. There was pipes leaking at a flange. Like, what the hell's going on? There was a check valve on the fill line for that tank, and there was supposed to be a weight and a spring and some adjustment so that check valve closes slowly. Either nobody put it on or it wasn't adjusted right. So that tank filled, and as soon as it filled, instead of that valve going, it went bang. and it sent a shock wave down that pipe through the water. It blew. There was piping leaking in manholes down the road. It blew shit apart everywhere. So this is a lot lower chemical, but it's the same thing. If this dampener wasn't here, it's this little high frequency shock wave that's being transmitted on all the liquid, right? So over time, every single threaded joint, everything in here, again, this pump can run it up to 200 strokes a minute. When you guys get your plant running, maybe you're not running that high, you're only running 50. 50 strokes a minute of every day, 24/7, no dampener. Hey you, hey you, hey you. It's like your little kid next to you. You're talking to your buddy. Hey Dad, can I do? You know, hey Dad, can I do? Yeah, hey Dad, what do you want, boy? It's like over time, that little teeny thing pounding, all of a sudden, why is this leaking? Why is this cracking? It's been sitting here getting just poked for a freaking year, 50 times a minute, every single minute. So the dampener really is almost, in my opinion, more important on these little teeny, pumps that put that pulse wave out. All right, I'm sure I bored you enough. Unless you have questions, it'll make a lot more sense when we have chemical and the valves are open. Like I said, I'm sure we'll be out several times again. We're going to be out to ring out the electrical signals, whether it's me or one of my guys. You see somebody out here and a question came up, just grab them. And then I'm sure probably when it's, go time and they're going to switch over to chemical, we'll probably be out too at that point, I would think, just to help verify settings, make sure everything's working right. And as questions come up, just
All the piping on these is Schedule 80?
yeah, everything's Schedule 80 on these systems here at this plant. Everything's Schedule 80 PVC. I'm pretty sure, I'll have to check on it, but I'm pretty sure we're using Viton on both of your systems here for the O-ring. Because that's another thing that's another thing with the skids in my company. It's like making sure we use the right materials. There's some chemicals where PVC is a fine material to use for the plastic, but there's also rubbers. Every O-ring and this bladder and all that, this has to be the correct rubber for your chemical. So for some chemicals we might have to go EPDM, for some we might have to do Viton, for some we might have to use Hypalon. So we make sure that, we'll build a Schedule 80 PVC system for caustic, for example, sodium hydroxide. It would look identical to this, but instead of Viton, everything would have EPDM in it because that chemical would eat up the Viton O-rings and would leak, just like if we made this one out of EPDM. But yeah, this is Schedule 80 PVC, Viton. On your sodium hypochlorite skid, your balls are vented. If you would pull one of these balls out.
Same thing with the diaphragms for the pump?
Well, the diaphragms luckily are, the diaphragms are Teflon. There's not a chemical I'm aware of that Teflon's not compatible with. So diaphragm is the same regardless of what chemical. Teflon's, if the manufacturers can make everything out of Teflon, they would, because it's the one thing fits all. But there's problems with doing Teflon piping. You can't weld it. It would be all threaded joints. It's real expensive, so nobody's going to do it. But the diaphragm itself is pretty bulletproof for any chemical. But same thing in the O-rings. When we order these pumps, if you look at the model number code on this prominent pump, it's like 20 freaking digits long, and they all mean something. It has to do with what kind of control functions we ordered it with, what the head material is, what the gasket material is. So same thing. This pump for bleach I might order differently for caustic, because there might be a model, one of those little model numbers or letters could be for what rubber is used for the O-rings, and that's where we might have to say, hey, on this one we want to use Viton O-ring, on this one we want to use EPDM O-ring. So sometimes in the check valves itself there can be a difference. On the prominent pumps, if you're not sure, right on the side label over here, and it's in our instruction manuals too, but you've got your serial number here, you got that 9 million code model number. It's also got the part number for the spare parts kit right on the side of the pump, on the pump label. So if you order that kit, that kit matches this exact pump, because it's printed on at the same time as the serial.
What about shafts? Is there any different materials?
Nope. Shafts are all the same, and the shafts are the same, and the shafts are not compatible with almost any chemical. So that's just, and again, it's because nobody would want to buy the pump if they did, and it would also be the same thing. Not every metal's good. So, like if I was going to use a metal for bleach, I'd want to use titanium. You're not going to want them to add a titanium shaft to this pump. This pump's already like $3,500. Now it's going to be $6,000. Plus, titanium might not be good for some other chemicals. So then they'd have to say, oh, we got some pumps with stainless shafts, some with Hastelloy C, some with titanium. So no, the shaft is bad. So what you can do, and I know how that is, pretty much all these metering pumps, if you put your hand back on the bottom behind the diaphragm on the bottom of the pump, there's basically a hole drilled, because again, on the front side of this diaphragm is your head, your check valves. On the back side of it, it's just airspace, and it's the actual shaft coming out of your pump that makes this thing go in and out. So that shaft, like you just asked, that's nothing special. That's regular steel. That thing gets hit with bleach, it's going to start rusting and corroding right away. There's a hole on the bottom of this pump, in between the head and the pump, there's a little teeny hole drilled. And basically it's just sitting there for two reasons. One, it's letting some air come in here, so we're not creating a vacuum back here. Air's just coming in and out. But if this diaphragm would totally fail, get a hole in it, chemical starts coming back here, it's going to drip out that hole and let you know the diaphragm failed. So if you ever come out here and you start noticing, hey, what's going on? We're getting bleach puddling down there. You know, the other thing, bleach is sneaky, creepy. It's freaking hard to find leaks. They're always coming from way higher than you think. Go up as high as you can and try and find any fitting that's got liquid on it. If you boil it down to, oh man, there's little chemical dripping out this weep hole right here, that's telling you this diaphragm, it might not have totally exploded. It might even still be pumping, but chemicals getting behind the diaphragm. I would shut it down, and I know how it is. It's Friday night. You don't want to deal with it. We got a backup pump. I don't have to rebuild this pump right now. You could try and let it go for a weekend, but you might also forget about it Monday, and then it's 3 and 4 weeks later and your shaft is rusted. If all you would do before you go home is shut this thing down, flush it, pull the head off, unscrew this diaphragm, and just hose it out real quick, you just bought yourself a lot of insurance. You can deal with it next week, but you at least hosed it down and got the bleach off of it. And the easiest way to remove a diaphragm pretty much on any pump, and these pumps are electronic, so it's different, but with pretty much every metering pump, you shouldn't turn the stroke knob unless the pump is running. There's very few pumps that'll tell you it's okay to not do that, but what you'll note, like on your other plant, you've got Sigma pumps. They got a big knob about this big, right, where you adjust the stroke. If you walk up to it and play with that knob when your pump's running, what you're going to realize is, like, say you want to crank it down from 100, it's going to be kind of hard to turn. And as the pump's running, you feel it get easy. Then it's hard. It's easy. It's hard. It's easy. It's hard. Well, it's as the pump's running, it's every time it gets to this kind of relaxed state in between the two strokes, it's taking all the pressure off the gearbox, and it's easy for that knob to turn. If your pump's turned off and you crank the knob, it takes a lot of pressure to turn the knob. And it's not that you screwed the pump up if you did it. You might get away with it. But what the problem is, in the assembly of that pump, somewhere down at the very end of that assembly procedure, somebody adjusted all that stuff. They got that stroke knob lined up where 0 meant 0, and it boils down to inside that pump, there's a double lock nut that locks all that stuff together. Now that shaft, everything turns together, everything's accurate. If your pump's not running and you go up there and it's like, I want to crank this down, and you turn the knob, it might work fine, you might be okay. But you also could run the risk of doink, you just broke that double lock nut loose. Maybe it wasn't tightened right or whatever, but all of a sudden you're turning the stroke knob and it might even, oh, it's easy now. Well, guess what? You just undid a lock nut on the inside, and all you're doing is you're only turning half of the picture. So you should only adjust the stroke knob when the pump's running, and the easiest way to get these diaphragms off is to run your stroke to 0, because 100%, like I said in my over-exaggerated thing, 100% diaphragm failure, anything below 100% is pushing the diaphragm further forward, okay? The diaphragm always comes back to as far as it can as set by the stroke length. So at 100%, it's letting it come back all the way. At 50%, you're not controlling how far forward it goes. It always goes all the way forward. You're controlling how far back it goes. So you're pushing it further into the head, so now it can only go this far, further into the head. So when you crank it to 0, what you've done is you've pushed it as far out as it can possibly go. You're basically pushing it all the way against the pump head. But that also takes the friction off the back side of it. So when you're going to remove a diaphragm, it's easiest to take the head, whether you do it before or after the head's off, fire your pump up, crank the stroke length down to 0% because you push the shaft all the way out of the pump. And now when you take the head off and you go to unspin this diaphragm, it's not being sucked back into the head. You know what I mean? This rubber is kind of creating friction on the back of the pump, and you're trying to spin it and get it off, you're kind of fighting it. If you put it out to 100% or 0% rather, it's basically sitting out here. Unspin it, regular left hand, right hand threads, unspin this thing, hose your shaft off, you're good to go. And that's something else we also do at our shop, just to try and help you guys out that I don't think other people do. We take all the bolts out of the pump and we take the diaphragms out of the pump when they come to our shop, and we put some Teflon grease on the shaft. So every one of these bolts has some grease on it where they go into the, they're just little brass inserts the screws screw into too, so those things will get corroded. So we've got Teflon paste on the threads on your pump head screws, and we've got Teflon tape on this here. So even if it does get attacked, hopefully we're helping you at least get that diaphragm off. Got a shot anyway. Okay, now any questions, or shut up, let us go home.
Not home yet. Any questions?
That calibration tool, what's that made out of?
That's just PVC as well. On these systems, we can get them in glass. So depending on the chemical, there's pretty much only two choices when it comes to these columns, is PVC or glass. Okay. So this is PVC, which is fine for this piping. If this was an acid skid we built, the piping would probably be Kynar, and we would have to go with a glass calibration column and pick the end materials and everything. And over time, bleach does affect it. Bleach will discolor it, make it brittle over time. Sunlight will, turn it opaque and yellow and get dry and crusty. So it is a replaceable item. They're pretty inexpensive. Odyssey recommends that, and it doesn't matter either way, but I don't know if you guys use Odyssey bleach or not, but they buy a lot of systems from us, and they usually recommend you don't leave chemical in the column, just because why have it sit there for no reason and wearing on the acrylic. So if you keep them dry most of the time, you keep them out of the sun, they'll last a real long time. But I think that thing's less than or right around $100, 2 or 3 years you need to change it. Oh, and something else, just so you guys know if this is in your head, because the girl, whoever answers the phone might not think to do this automatically because they're doing a lot of stuff. But another thing that we offer, we might charge you a few bucks more, but not much. But you'll be able to find some of this stuff where you could, I don't have to go to them to buy a back pressure valve or buy this. I could buy it from USA Blue Book or here or there or whatever. And that's true, you can. If you compare our prices are pretty much in line with everybody else. We're not trying to take advantage of anybody. But when you come to us, just like I said, what's the material? What's the bladder made out of? What's the O-ring made out of? If you come out of us and we get the serial number, we know that we're giving you the right materials for your job. Something else that we do, we charge a couple bucks extra for this, but years down the road, or maybe not years down the road, somebody said, hey man, I want to keep an extra one of these and an extra one of these in stock, so if I ever had to mess with it, I can just, because another thing we do that some people don't, you'll notice, anything on this system that might need to come out to be serviced or replaced, it's got unions on both sides of it. We want it to where that thing comes out, you're not out here with wrenches and pipe dope and glue, it comes out. So what we will do, if you were going to order a spare pressure relief valve for this skid, say, yeah, I want to have a spare pressure relief valve. If you say, hey, I got skid 2005. When your startup guy was out here, he mentioned that if I buy that valve for my skid, you guys can set it up with these fittings, and we will. We'll charge you a little bit extra because, just a couple fittings and the time of our guy in the shop. But what we'll do is we'll send you this valve, and we'll have taped and dope with the right tape dope. It'll have the right O-rings on it. It'll have the unions on it. So your maintenance guy doesn't even, we already gave him unions. So if he's got a new one of these in the box, great, but he's still got to take his wrench. He's got to unscrew these fittings. He should be retaping them, redoping them, and putting them in. We'll have it set up with those unions already attached to it. So literally in a couple of minutes, he can undo these unions, throw it in his toolbox, put the new one in, tighten the unions, and you're ready to go. So that's a real time saver. So basically what I'm saying, that you would get this, and it would have it would have, we know exactly where it goes. So this one, we're taking advantage of the union on the ball valve to be one of our unions. So one side of it has a regular union, the other side of it's a valve. But again, our guys would know by the drawings. If Debbie went out to the shop and said, hey, Marion County's ordering a back pressure valve, they want it set up for their skid. The guy would go look at the drawings and he would know, yeah, okay, on the inlet side I need to have a 1/2-inch union, on the outlet side I need to have a nut for an Asahi ball valve. And they'd send it to you that way, ready to go.
Can we drain this today? We're looking at 26 degrees Saturday night.
Oh, well, yeah, let's do that.
I mean, it's water, so it's fine.
Yeah, well, still, yep, nope. Why not? Yep, we can do that. I don't know if they have a drain. Yep, we can just drain it.
That might save us a phone call to you.
Oh yeah, nope. I'm all for. I'm all for not blowing stuff up. No, we can do that. What we'll have to do is.
You can take the unit loose.
Yeah, well, either that or we can use our flush.
Yeah. But then you didn't. Feel better now.
All those are threaded fittings you put Teflon on?
Well, we actually use a combination of, and it's crazy. If I had some with you in the truck, yeah, we use Teflon tape. Every threaded fitting, we use a combination. We use Teflon tape, and we also use a Teflon-based pipe grease over the tape. So, yeah, it's like a pipe dope. It's very, yep. I'm going to do it out of every pump.
Well, I'm seeing 22 pounds of pressure.
Yeah, well, that was from me running it yesterday. So right now, that tells us your pump check valves are working good because.
It didn't bleed down.
Yeah, yep. I was out here playing around with stuff, and I shut your pump off, and basically, between that closed valve and your pump check valves, it's holding some pressure. So what we can do now the unfortunate thing is that we get some water in your skid, but we'll dry that all up when we come.